Hi, everybody. So today I want to start talking about an area of physics called geometric optics, also known as ray optics and sometimes geometrical optics. This is going to be a case where we start to study how electromagnetic waves interact with matter. And again, what we've been talking about is laying out what are the basic properties of electromagnetic waves, that they're disturbances in the electric and magnetic fields that propagate in various ways and can carry energy and motion between charged objects. Now, what we're going to be dealing with today is a case where we can make some very simplifying approximations. Basically, rather than having to think about this as a wave with a wavelength and with a frequency and with electric and magnetic fields pointing in a particular direction, what we're just going to think of is that this electromagnetic wave is basically just something that carries energy, etc., between a pair of objects along a straight line, which is a decent approximation a lot of times. These things are typically called rays. You know, we start at one point, we end at the other, so there's definite direction because these disturbances go in a particular direction. But we're going to not think too much about the detailed structure of it. We're just going to think of it as something that carries energy or light in one direction from one object to another. Now, this picture where we literally ignore the wave-like nature of these things, it works reasonably well when the size of the objects you're talking about and the distances between them are big compared to the wavelength of the wave. If the wavelength of the wave starts getting comparable in size to the objects or the separation between them, then these approximations we're going to talk about start to break down. You can't just think of light as just traveling along straight lines between 2 points. We'll talk that at the end of this section, we'll consider those scenarios. But for now, it's a decent approximation. It's not perfect, but it's a useful place to start to understand how these electromagnetic waves can propagate and how they interact with matter. Now, one important thing about this is you should know when it's reasonable to do this. So, for example, a reasonable question is, what type of electromagnetic wave is geometric optics a reasonable approximation? Is it a good approximation for radio waves, infrared, or visible light? Or is it equally likely to be valid for all of these cases? In practice, it turns out that visible light is often a case where this is much more likely to work, just because visible light has the shortest wavelength. So we are in a situation often in our own day-to-day experiences where the size of objects, physical objects we can hold in our hands, and the separation between them is big compared to the wavelength. So the approximations usually hold fairly well for visible light. For radio waves, often the wavelength matters, and this is often a less good approximation in most practical cases. Infrared is kind of in between, depending on which type of infrared you're talking about. So this is going to be a place where we're going to talk more about light than, say, radio waves. Okay. So what we're going to talk about now is how light propagates. At first, it might sound like it's straightforward. It goes in straight lines. But what's important to understand is we're still going to be interested in how light interacts with material objects, how does light, reflect or transmit through different materials. So what we're going to be talking about is what happens when light interacts with mirrors, with lenses, with other objects. How much of light hitting the surface gets scattered in different directions. Now, it turns out the basic rules that govern this do depend on the fact this is an electromagnetic wave and that the electric and magnetic fields are interacting with the matter down here. But from those detailed interactions, some basic rules appear. And those rules are things you can use that don't require you understanding the detailed interactions between the light and the material. So the first of these we're going to talk about is the rule or the law of reflection. The law of reflection, and again, I'm going to say this here because I might have forgotten, I hate terms like this. There is no legal requirement that light behaves in a certain way. This is an observed property of how electromagnetic waves interact with matter. It is given the name law of reflection for reasons. What the law of reflection says is that in a specific situation where you have a completely flat surface, that if you have a light ray that is incident upon that surface from one direction, so it's coming down this way, the light reflected from that surface can only go in one direction. So if an incident ray comes in one way, the reflected ray has to go in one other particular direction. And that direction is specified in a very specific mathematical geometric way. The way we express the directions of the incident and reflected rays is relative to what's called the surface normal, a line drawn that's at right angles to the surface. So if you have a flat surface, it points straight up. And basically what matters is what is the angle of the incident and reflected rays to that surface norm. And it turns out that this angle, which is the angle of incidence, which is the angle between the incident ray and the surface normal, that is just something that depends, that number equals this angle, which is the angle of reflection, which is the angle between the surface normal and the reflected ray. So if you know what the incident ray, how the incidence ray came in relative to this line, you immediately know where the reflected ray is going to go. Now, if you have a question of, really? Why does that have to happen? That's a very good question, and I wish I could tell you. Turns out, this is a fundamental result for electric and magnetic fields. It is not specific to any type of material or anything else. It is just the fact that the surface is flat. And it arises because the electric and magnetic fields from this particular wave pull on the charges in this flat surface in a very specific way. And those moving charges that start sloshing back and forth produce radiation that can only go in one direction if the surface is completely flat. It is a fun example of what's called matching conditions, when you have to basically figure out what's happening at a completely flat interface. It's cool. It is well outside the scope of this talk or this class. So, but it's a rule, and it's a rule you can rely on. Now, this rule has some important implications. For example, if we imagine we have a completely flat surface that obeys this rule, and we consider a couple of light sources, one green and one red. The one green is fairly high up, the one red is fairly low down. If we look at this surface with our eye or any other instrument, if we look down at this point in the mirror, we can see light from the green source. The light comes down at a steep angle, bounces up at a steep angle. If we look further down the mirror, over here, we see the light from the red source. It comes down at a short angle and bounces up at a relatively shallow angle. The important thing to understand is, if we're looking down at the mirror, this is the only place where the angle of incidence and the angle of reflection match. If we try to do this with the green source here, it would come down at a steep angle and bounce out at a shallow angle. That's not allowed. So if we look here, we only see the green source. If we look here, we only see the red source. So when we look at a mirror, we can distinguish light coming from different places. That's the basic nature of a mirror. You can see things in the reflected light. You don't just see a broad haze, you're able to distinguish particular sources. In fact, you could figure out how you would see this fairly straightforwardly. Since these rays bounce in the particular way they do, you could get the same pattern of light reaching your eye if you took each one of these sources and basically flipped them below the surface. So you take the mirror, remove it, but take all of the sources and move them an equal distance below the plane of the mirror. So you move this one down a little bit, you move this one down a lot. These things would produce light that would reach your eye just like they do here. This is an example of how an object can produce what's called an image. It's basically why what we're not seeing a mirror, we're seeing things around the mirror. And we'll talk more about this when we talk about things like lenses and other objects where this becomes quite relevant. But this is why when you look at things where this is true, reflective surfaces, you can see images, you can see a reflection. And the key thing to understand is this rule holds for any flat surface. It does not care what that surface is made out of, it just has to be perfectly flat. This is why you can see reflections in lots of different materials. For example, you can see a reflection in a mirror, of course, most of which are metallic, but you also can see reflections in glass, in a window, like when it's dark outside. Glass is a very different material from metal, but they're both able to do this because they're flat. Now, the thing to understand, of course, also, is that this doesn't happen for every material. If you look at, say, paper, it's pretty flat, but it doesn't reflect like that. If you hold light up to a sheet of paper, that light doesn't all go in one direction. It gets bounced in a variety of directions. In fact, most surfaces do this, because if you have a light on in the room, you don't just see spots of light, you see light no matter where you are. This is for a couple of reasons. The one that the book focuses on, and one that is relevant, is surfaces like this aren't perfectly flat. They have hills and valleys on them. And each of these hills and valleys does reflect light in accordance with the law of reflection, But since different parts of it are tilted at different angles, some of the light can go up, some of the light can go this way, some of the light can go that way. That's an important rule. I will say it's not the only part of this. The thing is, something like paper, the light doesn't just bounce off the surface. It also, some amount of light goes in. We'll talk about this when we talk about refraction. As the light gets into the material, it starts interacting with various parts of the material. It can bounce around in various directions until it reaches the surface and then it comes out again. This is another way light can get redirected in a bunch of different directions because it's where pores are, where the threads of the paper are, et cetera, et cetera. It makes things just that much more complicated. If light can get into the material, things get more complex. And this is one of the reasons why mirrors are really good reflectors. Mirrors are good reflectors because they're conductors. Conductors respond really well. You know, conductors have electrons that can move really easily. They respond really well to these oscillating electric and magnetic fields. They are very good at basically reflecting all the light, not letting any of it into it, which makes these things very good at this. This is why most mirrors we're familiar with are in fact metals. But you can make them of other things, and there's oftentimes you want to do that. Okay, so that's the kind of concept stuff I want to talk about for today. For the next video, what I'm going to do is go through in a bit more detail how you approach problems with this sort of, where we have to deal with the law of reflection. How do we actually use it? And the specific case I want us to consider are things called retroreflectors. These are just something that bounce light straight back in the direction they originally came from. These are things found on, say, bikes and other things, various signs and such. And there's also a very interesting one that sits on the surface of the moon. And I'm going to talk about this because this is a nice practical example of why understanding how the law of reflection works is useful.